Okay, guys and gals, let's start today's session. I've been busy trying to make matrix multiplication work with Cutlass. I've been having various regrets. The last week pretty much started with me making this post, and when I didn't get an answer, I decided to put some effort into getting Cutlass to work. I made this issue like 3 months ago, and over here I finally managed to get Cutlass examples to install. I can, for example, show you. I also have a video on my channel which shows how to actually get this to run. So it's not a big deal. And right now we can pretty much run most of the examples here. Like this one, for example. And okay, if you wanted to get rid of the type errors, all we have to do is go into Cuda, copy this, put it here, and this is currently the level that I am at. And now that I am able to compile all the examples and run them, I thought the things would be easier, that I'd be able to just go in and get Cutlass to work. So I can replace the matrix multiplication kernel that I built myself in the machine learning library. And as you can guess from the way this is going, I didn't really... things weren't going according to plan. I ran into various bugs, and this one is, fucking amazing. I mean, I made this example, and basically this entry kernel, when I compile it with this include for the Cutlass gem device, gem universal adapter, it cannot find it. And rest assured, this name here is the same as the name in the kernel. That isn't the problem. And I opened this issue, I opened it also on the CuPy repo. The CuPy guys investigated it, and they made this minimal reproducer. So we just have this include, and we have this entry function. And what's happening that once this program is compiled, this function ends up being dropped in the what? In the sample Cubin file. And I'm guessing this is the PTX binary file that the Cuda compiler uses to actually generate the final level assembly. And I went ahead and opened an issue with NVIDIA for this because I really doubt that this is an error in the Cutlass library. It's most likely some kind of compiler error. I mean, I cannot possibly imagine that C++ would have a feature which would end up dropping other externs. It just doesn't make sense. So next week we're going to probably get a reply from the NVIDIA developers and the Cutlass developers. And besides that, what I'm having trouble importing here is just this gem universal adapter here. This is a device API function. I'm also trying to open a kernel API function, and that's the types in those functions, the classes, are for use in the kernel directly rather than the host. The device API functions are used on the host. And if you look at the various Cutlass examples, you'll see that, for example, let me show you. Let me just show you the quick start. It kind of ends up looking like... this is the example that I wanted to show you. Launching a junk kernel using Cutlass 3.0 or newer. You can see it importing this device gem universal adapter. Then it also imports the gem universal kernel. And here they instantiate a bunch of types. They have this main loop here. And then they get this kernel class, and then they also, instantiate it. And then they pass it into this gem universal adapter, this gem kernel class. And if I could have gotten this example to work, that would have been absolutely perfect for me. But I find actually getting this to compile to be impossible. Even the examples that are in the Cutlass repo are impossible for me to compile. And I did that in the issue here. Like, I basically am trying to get this gem universal thing to actually include, and I'm having a lot of trouble. As you can see, this is what I get in the IDE. Even though I have the right includes, it doesn't work. The one in the test harness does, but this one doesn't. And I have no idea what fucking command line options I need to put in the IDE or somewhere else. This whole experience is really showing me what's the difference between something like a .NET library and a C++ library. In this C++ library, you have a folder and you have 100 different files, and you have to pick them correctly manually. And the whole library is basically C++ templates, and they have a lot of variations for different. They have a lot of overloads. So this library is pretty much made of overloaded templates, and it's pretty much impossible to follow. Like, I could go into here, and of course I could go into these header files, and let me show you, for example, what happens if I go into let's see, where is the gem? Oh yeah, here it is. If I go into here, and if I go into here, it pretty much looks like this. Every single template has like okay, let me count. It's 527, 569. So it's like what? At least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. This template has 22 arguments. And I am expected to actually, follow this. And the problem is that this is like a device level function, and immediately at the outset, I'm faced with pretty much the entire internal level API. It's very difficult to, even though this has comments, which is better than nothing. It's pretty much impossible for me to follow this, and unless I want to spend a month or two studying this library. And it's not just this one single gem class. It has a bunch of these gem classes for different specializations. This one is for permuted layout, and if you look somewhere else, there'll be a bunch of other classes, like whatever. Anyway, if you look at the containing folder for this, there are like a shit ton of these different device level gems. So good luck trying to follow all of that. Like, if you go into the kernel, yeah, they're not a. Okay, how many files are these? 90. Yeah, basically, good luck trying to pick which one to include. I know which one to include because the author himself told me. I need the gem universal. But if you look here, I tried getting one of the Hopper examples, which actually are using the gem universal thing. Like this thing here. Yeah, as you can see, it's I'm trying to import this gem universal thing here, and I'm getting type errors pretty much everywhere. And this is not some example that I made myself. It's one of the examples in the repo itself. Like, let's see, I think it's this one. I mean, a lot of these Hopper examples are using the latest API. Okay, as the first step, we have to go into here. And yeah, now most of the type errors go away, but we still have the type errors for this. And I'm not sure what exactly is the problem is here. Maybe I'm missing some include somewhere, but who knows. And the biggest problem is this. For some reason, this is not defined anywhere, even though I've actually tried compiling the Cutlass repo with the support for this in the past. And if I get rid of this, and if I get rid of this, yeah, I get these kinds of errors. And you have to keep in mind, this is not some example where I started my own project and just copy pasted the code. This is the example in the Cutlass repo itself, and it basically doesn't work for what I wanted. And I'm pretty much stuck on this. I'm not an expert in C++ build systems, and neither do I have the interest in it. And if you look, even if you look at these command line options, there are a shitload of them, and I'm not sure whether I find it acceptable to even try to use Cutlass when I cannot simply just include the headers and use it in that way. So basically, I'm not going to disparage the author's work. I mean, I personally wouldn't design a library with overloaded C++ templates ever. But he's working in C++. So he has to make the best of his situation. I won't fault him for that. I won't. The library could be. I could have some nitpicks about him using void pointers in places and so on. But whatever. That's not really why the library is so horrible right now. The main problem that makes it unusable for this, for my own purposes, is this. Basically, I cannot go in and include some headers and try to import the functions because that process simply doesn't work. And I am pretty much begging for mercy here in this issue. So to me that is unacceptable. And I've been depressed over this for the past few days because, since I got the examples to run, I thought that I'd have a much smoother time actually using this library. But we are going to have to treat this much like I'm treating the Croatian healthcare system. The Croatian healthcare system has competent doctors, but they cannot assume that you have infinite time and that you can pretty much wait forever for treatments. So while we wait for the Cutlass author to treat this issue, we're going to have to work on our own multiplication kernel more. Even though we got it up to like 60%, we're going to bring that in fact down to 50% utilization in order to free up some registers, and we're simply just going to use that. And what I'm currently working on is this. I have a bunch of regrets for from where the last video of the matrix multiplication ended. As I say here, I got stuck on a certain step in the last video. I couldn't get these asynchronous Ampere loads to work last time. So I've been making some test examples here. Let's start with the first one. Here we have a very simple map kernel. This is pretty much copy-pasted from the primitives module. And I basically just run this, and it's kind of takes in an input, multiplies it by 10. And now what I'm looking at is, how the nanosleep function affects the computation. Like if it's commenting out, what the nanosleep function does is it suspends the thread for a duration of 300 nanoseconds here. It has a limit of about 1 million nanoseconds, but that doesn't matter. I'm basically just observing how this changes the memory occupancy. This nanosleep function. You can imagine this as being some kind of expensive computation. Without the nanosleep, I get for this map kernel, I get 92% memory occupancy and 2% compute occupancy. So it's mostly memory bound. Once I turn this on, the memory occupancy goes from 92 to 37%. And over here, I'm actually gone ahead and change the map kernel so it actually uses pipelined loads. What that does is, instead of just loading from global memory into registers, it instead first loads it into shared memory using the asynchronous loading instructions that the Ampere GPU has. What we're doing here is basically just using the Cuda pipelines. Yeah, we're using the producer acquire, producer commit, consumer wait, consumer release. It's kind of similar to this. Right. This is producer acquire and producer commit and the Cuda mem copy async. That's pretty much what we have here. We have this producer phase and the consumer phases. And if you look at how this is implemented, it's not that complicated. Well, let me show you. We created this back in the matrix multiplication kernel, and I am revisiting this after 6 months. Yeah, so we just wrap the producer acquire, producer commit in its body, and the same for the consumer phase. It's a bit safer like this. Not really a problem. So let me just open it up again. If you don't make any changes to the file, and go into a different file, it will close it. So we also have this look ahead loop, and let me show you again what this does. Okay, first, actually, let me just cover this. We're first taking this input output tensors. We're factorizing the innermost dimensions into chunks of 4, and then we are also factorizing the leftmost dimension into chunks of threads per block. Over here, that would be 256. So if we did a print static, you'd see the. If we did a print static like fan x print static x dim, what you'd see is first the outer dimension, then the middle dimension would be 256, and then the last dimension would be 4. Here I'm doing some reordering, so the outer dimension is in the middle, and then right away I'm just applying the thread index. I'm also creating this shared tensor, applying the thread index to it. And these are the local arrays. And over here we just apply the outer dimension, and then what this has is only the innermost chunk, which is of size 4. And we can use this to do the asynchronous memory copies. And this is just the regular map over the stuff in the local tensor. And then we just, at the very end, we do a synchronous memory copy into global memory. We aren't going through the shared memory for that. The reason for that is because the Ampere has the asynchronous loading instructions, but it doesn't actually have the asynchronous store instructions. So there's no point in going through shared memory for that. And in this over here, I'm kind of right now my confidence is very low. I thought that maybe that I'm completely confused about how the asynchronous loading should work, and I'm just doing basic sanity checking here, like whether this works at all. So sorry, let me also just cover the look ahead loop. It's not very complicated. It's pretty much it's very similar to a projective loop, but instead of just passing in the index into the body, it also does a check whether it also passes a boolean whether the iteration of the loop is the initial one. It does that by checking this initial index with the current index. That's a very simple way of doing it. Over here, we are doing a projection of the. Wait, what? Oh crap! I mean, okay, this is a bug. Project near to from, and I think instead of doing that, it should be projecting the I, not the from. Oh crap. Okay, so this is a bug, and and it has been caught in testing. Okay, it's very good that we figured that out here. Okay, I'm very happy that I'm actually trying to explain this loop to you, because we discovered this bug. And the reason why I haven't realized that there is a bug is because I'm only printing out the first 16 elements, and on that this loop would work correctly. Silly me. Anyway, what this does is simply projects this integer index into the high dimensional space that's given by the near 2, that's bound by the near 2, and we get the actual index there. And this actually gets the index of the next loop and projects that. So this is like the I on the next iteration over here. And if you look at what's happening here, on the initial phase, we first do a asynchronous memory copy into shared memory. Then we copy from the shared memory to the local memory. And then, after that has been done, if there is a future I, if if there is if you know if the future I actually doesn't go beyond the edge of the array, what happens here is that we do asynchronous memory copy for the next batch of data. And we do that in order to interleave the loading with the computation. We do that right here before doing the computation in the loop here. And this is basically how I've tried the structuring the matrix multiplication. I load the data into shared memory, then I do the matrix multiplication. But before that, I also do the loading for the next batch of data, while the current batch of data is stored in registers. And I couldn't get 6 months ago in the last video, I couldn't get this to work better than asynchronous, the loads. So what I'm doing right now is investigating why that is the case. So I did a one experiment. Like my mindset up until yesterday was that I'm doing this completely wrong. But so I made this, and what I will try doing is basically disabling this. No, it's not like that, but like this. And I put this assert here. And if we compile this like so, with the producer and consumer pairs commented out, we in fact do get the error to trigger, because I realized that through logical reasoning that if I'm really actually doing the asynchronous loading instructions wrong, what would happen is that the reads themselves wouldn't work correctly. Like if we really got this part wrong, then what would happen is that this part would try to execute the stuff in local memory before the asynchronous transfer has even finished. So the fact that this works means that the asynchronous transfers do in fact work, because if this, for example, didn't work, we'd get the incorrect result. The assert that we have here simply would fail. And right now, if we try to compile this, it doesn't. So yeah, I do think that we have in fact gotten the asynchronous loads to work correctly. It's just what's going on is that for some reason, even if we use synchronous loads, the Cuda compiler is actually very good at interleaving memory loads with computation already. So that's why we aren't seeing any improvement in the matrix multiplication kernel. Let me show you something. Like, okay, let me comment this out. We're going to comment this nanosleep instruction out, and then we are going to run this. This array has 250 million elements. And since this is a 4-byte float, that means the entire array takes up a gigabyte of space. And there is also the output array. So what we are doing here is doing a map over arrays. We are doing a map over a 2 gigabyte space in total. We're basically testing how fast it is at reading and writing to 2 gigabytes. Let's build this file, and we're going to go into Nsight Compute. And I already had a project that I'm using to test this. Ignore the results that are here currently. And we're going to evaluate test1py. For some reason, it refuses to exit the terminal even after the process finishes. So you just need to press Ctrl C here. Okay, and this takes 11.45. Yeah, now it's actually... Yeah, yesterday for some reason it was 7, but right now it's 11.45. And this is in milliseconds. You can see duration milliseconds. And the memory throughput is... Yeah, it's a bit lower today than yesterday for some reason, but never mind that. It's at... Yesterday it was at 92, here it's 87.6. But it's close enough. Once we actually put the nanosleep instruction in here, what will we get? Here it is 11.45, and the memory throughput is 87. With the nanosleep function, what happened last time is that the duration went up by 3 times. And memory throughput went down by 3 times also. Something like that. I'm shutting down manually. Oh yeah, the duration is now 25.37. The memory throughput is 37.95. So yeah, it's the nanosleep function is intended to emulate some kind of intense computation. So even because the nanosleep functions, instructions aren't counted as computation, the compute throughput didn't go up. But if it was actual computation, it would have gone up, while the memory throughput went down. Okay, so this is so far so good. Let's try doing test 2. So I thought maybe that this would end up because it's no longer waiting on for the memory loads for the next batch to finish, that it should be faster than the first example, but that's not what I got. Or here you can see that the tensors have the same size, we have the same nanosleep. The only thing that we're doing different is asynchronous loading the data into shared memory first, and loading the next batch of data while this is but the first one is being computed on. So I built this. Now let's try running it in Async Compute. I think we should get the same duration, but surprisingly the memory throughput will go down, and by a lot. I think it should go down to 20. I'll cancel this manually. Wait, did I forget to actually change it to test2pi? So the memory throughput didn't go down at all. The reason for that is because because we fixed that bug in the look-ahead loop. I thought the memory throughput went down because the asynchronous loading instructions, and I couldn't really explain why that would be the case, but it was because of the look-ahead loop. And yeah, the duration here didn't change much. It's still 25 point something. So the duration is 25. I thought, that we didn't see any improvement. I thought, this is basically the same what I ran into with the matrix multiply. I have a synchronous version, and that shouldn't be interleaving loading with computation, and then I do a asynchronous loading version, and I don't get any improvement at all, even though it should be faster due to interleaving the global memory loads with computation. So what I did here, I made an example that only has a nanosleep instruction. Let's make it let's make it 300, just like in the previous examples, and you can see the loop size is the same as the tensor size previously. It's 250 million roughly, 2 to the power of 28. So if we compile this and then run it, then what will we get? If you recall, when we did that original map without the nanosleep instruction, we got a duration of 11. When we added the extra computation in the form of when we added a delay in the form of nanosleep instruction, the duration went up to 25. What do you think the duration should be here? I thought it would be something like, because it went up, because yesterday it went up by 3 times. I thought it would be from 7 to 21 to 22. I thought maybe I get a duration of 14. So over here we should be getting also roughly that amount. Instead, what we'll get is 25, I think. 23. So the duration only improved from 25 to 23. In other words, the entirety of the kernel's runtime is taken up by the nanosleep instruction, and whether you use the asynchronous loading or the asynchronous loading, you get the same duration. The Cuda compiler is insanely good at interleaving memory loads with computations even natively, and my optimizations didn't make any difference. I'm very shocked. So I think I'm going to pause here and do some more research on my own. And the way we are going to improve the matrix multiplication kernel, if we go into the previous video and check it out, you'll see that that because we are unrolling one of the loops. Where is it? I'm looking for the matrix multiply. It's in the ML library. Yeah, well, let's see one of the loops. Okay, not this loop. Oh yeah, we have the pragma roll here, and we are unrolling this K loop, and that's not that's not something we really should be doing, because when we did this, this is one of the middle loops. So once you actually unroll this, it really blows up the even though it improved the efficiency, even though it actually improved the performance of the kernel by something like 15%. It also blew up the generated code by 4 times. Something like we had a matrix multiply kernel will be something like 4,000 instructions, and after this it was like 16,000. So, and it ended up consuming pretty much all the registers, whereas previously it would be like something like 180 registers. Once we unroll this, it goes up all the way to the maximum, which is 255. And we're having the same problem in the machine learning library because of that. It ends up taking up too much registers. So the way we actually, to prevent it from being unrolled, all we have to do is, just do this. And now this thing inside here won't be unrolled anymore. And I think for the stuff inside here, we do want to yeah, unroll them. Yeah, the pragmas are a lot easier to use in a spiral than they are in C++. If you do a pragma unroll here, it will put in an unroll for every loop that's inside its body. We have a special code generator support for that. We have implemented that back in the matrix multiplication series. And I'm not sure whether this is everything that we have to unroll. Let me actually undo that, because we have to actually check out and test whether the unrolls make sense. And we're going to do that later. But what I'm doing now is basically testing all this out. Whether the asynchronous loading instructions work. I want to understand better what's going on in the Cuda kernel. The first, I also want to make an optimization for the look ahead loop. If you look at the Cutlass repo, there was an interesting discussion posted, like Cutlass. It has a discussions page. Okay, let me pause here and I'll find the discussion that I want to show to you. This is the one. How register liveness reducing is achieved. Helper to rematerialize block index reduces register liveness. And this is a very good explanation. We have, instead of move block index x to a register and then 1,000 lines of assembly, and then making use of it. What they're doing is basically getting it directly. And you can see me is cursing. I was really hoping that the Cuda compiler did that optimization on its own. And in fact, yeah, I can't think of many places in the ML library where I failed to apply it. I got an up error, but even if I hover, I cannot see who gave it to me. No, never mind. So yeah, I really fucking hate Cutlass. Cutlass's build system, but it's not like what I did in the matrix multiplication series. It did have the reason of me needing to implement the tensor module, and I did need to at least get some exercise in GPU programming, and I did need the matrix multiplication kernel. But even so, actually implementing it on my own for actual use and taking 2 months to do it is pretty fucking insane. I mean, there's no other way to describe it than that. A sane person would definitely use the linear algebra library that the experts have developed. But right now, Cutlass is simply so damn difficult to use. I'm completely stuck. And the only hope is that the author the authors will give me a hand to actually somehow bring it into the Spiral machine learning library. I cannot completely rely on them though, and even though I cannot go probably as far as they can when it comes to optimizing the the matrix multiplication kernel, I can go like 80% of the way there on my own, because even though matrix multiplication is complex, it's still just like a couple of nested loops, and I'm not so incompetent that I cannot do that. And I have in fact done that. And the matrix multiplication that we do have in the library, once we kind of optimize it just a little, will be pretty decent for our purposes. And after that, whether the authors come in and help me, or whether or if they don't, depends up to fate. So what we're going to do now is work on that rematerialization optimization. And the way to actually implement it in the library is pretty simple. Okay, first of all, let's take a look at the look ahead loop. Where is the loop module? Loop. Oh, here it is. Oh, damn. Excellent. Impressed. I already had it open. Yeah, I mean, who's going to keep track of the tabs? It's better to just close them and then to open them again. I cannot understand people who have like 30 tabs open. So, okay, so here we violated that basically that rematerialization principle. We have this I plus by bound to a variable, and this is my usual programming practice. I don't want to copy paste what could be bound to a variable, but it seems like this is working against my instincts here. Okay, let's check it out. First, we're going to try copy pasting this into here and here. Okay, first of all, let's do. Oh wait, not this here, but here. Let's build a file. Let's run it in Async compute. Right now we still haven't optimized it at all. I want to see how many registers are being used. It keeps failing to disconnect from the process. 32 registers. We'll take this. Actually, let's just do it like this. What the hell? Yeah, and now we have the type errors in all the right places. Actually, let's do it like this. Did you know you could do something like... Oh, wait, I didn't mean to do that. I meant to do... Yeah, like this. Yeah, you can put a inline statement like this into an expression. And sometimes, I very rarely do that because it ends up taking too much horizontal space. But in places like these, it can be useful. And now, because we are doing it like so, it won't end up holding on to this variable, to this future I variable, to this I code variable. It's a function, and we're only materializing it where we need it. It's a simple addition. And we're also doing a check whether I is from, and this is going to be held in a register. And we also want to turn this into a function. For now, let's just try saving this. We're going to build the file, and then we're going to run it. I mean, if this saves us a single register, then it's a success as far as I'm concerned. Maybe I should switch to basic instead of full profiling. Yeah, and the number of registers didn't go down at all because I think the compiler is in fact doing this optimization. I mean, we could check whether the source itself is any different. Trying to go to the end. It has 288 instructions. Could I maybe just copy this somewhere? Oh, okay. Oh yeah, we can copy it like this. Okay, let's do a diff online. Diff online. Okay, here we have this. I guess it has a lot of white space. That's why it's looking like this. Now, let's undo that. Let's undo this optimization. Okay, let's undo this. Yeah, did we build it? Okay, we built it. Now we need to run it. Okay, let me think. Let's run it. We're going to change the metrics to just basic. And as you can see, this white box issue is very annoying in Inside Compute. I did open an issue regarding this, like, let's go to developer NVIDIA page. If you ever run into bugs in your when you're doing GPU programming, just open a bug here. Actually, very often you do get replies. As you can see, he's saying that he can reproduce the white box, so sometimes it's random to him, and they'll keep me updated. Also, in the past, I opened an issue, for example, inside Compute, that I wanted, to analyze register leaks, and I also got a positive reply that this will be added in Cuda 12.7. So they are listening to me. You can see some. I made this open this GitHub issue. And you can see some screenshots here. So yeah, if you can just do open an issue like with on NVIDIA support, because they need somebody to tell them that there's something wrong with the tools. Otherwise, they won't know. I had this issue like 6 months ago, and it hasn't been fixed. So this is why I opened this issue. In fact, I do recommend like. Let's go to Reddit just for a bit. You can see this guy. Where is it? Is it really? Yeah, it's. I mean, sorry, I'm getting distracted. Yeah, compilation with G hangs forever. I guess this guy is running into some exponential compilation problems, and I've been also having those kinds of issues with that game. But the game that I sent to them is very large, so it's going to demotivate them from investigating. And yeah, so here I tell them to make a minimal example to and send it to NVIDIA. So if you yourselves are running into those issues, open an issue so the others can benefit, even though it's kind of unpaid work. So let's finally run this. And we're going to take the source and we're going to paste it. Like, who knows, maybe the number of registers didn't go down because they are getting reused somehow. Whoops, I didn't mean to do that. Sorry, I meant to press Ctrl C. And we're going to go into the source. We're going to select it. Okay, let's try find the difference. Oh, really? What's the difference? C, move around C. Okay, this is kind of, I don't know, confusing. Like, I cannot really see any difference, even though there are differences. Okay, let me pause here so I can study this for a bit, and then I'll come back to you and tell you whether there have been actual differences. Okay, I don't know why, but the format of this is completely different from how it was before. I'm definitely confused why this is happening. I guess, okay, let me just try copy pasting this again. We're going to put this here. Yeah, now we don't have the white space anymore. Okay, so let's try compiling this again. This time with the optimization. I've just redoed all the changes. Build file. Oh yeah. This is happening because now we are using the basic metric. That's most likely why we are getting so much difference. Oh great. Okay. Now, are there any differences? Yeah, they are. Okay, this is a difference. Register 8. I mean, the register usage is the same, I guess. I'm not sure what this is. Oh, yeah, this is probably the blocks per thread, but no, it cannot be the number of blocks per thread. Register 8, register 8. I don't know. Okay, let's go. Let's try just pursuing this all the way to the end, and we'll see what happens. Whether we can lower the number of registers in use. We're going to go into the range M, and we're going to change the type, this range. And okay, let's go into the loop. And this is going to be, we're going to change this so it's a function like this. And we're going to just try rematerializing it everywhere. And this is pretty much the reason why I made the change. So we can change this from I equals from to I equals from parentheses. Okay, let's see. Okay, let's close this. Now let's see. Loop. Yeah, we have to go into range M, most likely, and we're going to have errors everywhere. And we have to now turn this into functions. And you can see where we're doing this just for the from, because in order to actually calculate the thread index, it has to first get the value from registers and then do arithmetic operation. And I probably should have made a commit before doing this, but never mind. Lock index. Okay, now let's see whether we have... Yeah, we have problems everywhere. Tensor main. Oh yeah, maybe this might... I mean, okay, we aren't using this anywhere. I mean, that particular run. Yeah, there's something I've been really thinking about. I mean, maybe I'm talking about this a little, and it doesn't really have anything specifically to do with what we are working on here. But I remember watching at least the first part of the video by Eric Schmidt. That leaked Google video where he talks about AI, and he kind of keeps talking about arrogant programmers. And now I've read a certain article, like, let's see. Actually, I don't want to open my private journal. Founder. And I found this, I found this to be interesting. And basically saying here, there's a key paragraph in his SH, which I think shows this. Hire good people and give them room to do their jobs. Sounds great. When it is described that way, doesn't it? Except in practice, judging from the report of founder after founder, what it often turns out to mean is hire professional fakers and let them drive the company into the ground. So between this and Eric Schmidt talking about arrogant programmers and this whole AI chatbot thing where they are promoting them as replacing professional programmers, I cannot help but think there's some kind of war on engineering by the basically salesmen. And I found this. I basically don't understand this, but that might be because I'm very rarely actually doing programming jobs. So how do I put it? It kind of feels wrong to that. The management would treat engineering like this. I don't know where this kind of blowback is coming from. I don't understand it at all. If you understand this yourself, do post a comment on YouTube. I'm kind of going through some stuff where I tried promoting Spiral. You know, I do have some pride in the work that I'm doing, but I kind of do get the sense that I'm a piece of garbage in this kind of environment. It's like programmers are like a grass, and I'm pretty much treated like that. And over here, they're basically saying, yeah, if you are hiring professional fakers, that means you are a poor manager. I mean, this much is true, but given the sheer quantity of people trying to enter the field, I'm guessing most programmers are fakers right now, and the managers cannot separate them out. So this is very unfortunate for me, and I don't know what to do about it. I'm pretty much doing this. You know, I do have this YouTube channel. I do have my own programming language. I do have my own projects in order to send a signal that I'm actually good. And as far as I can tell, it's not working at all. I honestly don't know what to do about this, but to continue working on my own projects. I mean, okay, I can. If people aren't looking at my own projects, I did have this reasoning that I could, pretend to be from Google or from some large company and, getting that way. But as far as I can tell, after 2 years of a bad job market, I think pretty much everybody who's bad is doing that, pretty much lying their ass off. So I cannot get an edge that way. I think at some point, having a shitty resume will start being a signal. Again, at some point, people need to wake up and do proper candidate evaluation, because just because you're getting like hundreds of applications to your job doesn't mean there are really hundreds of people wanting to work at your place. It's kind of like in the dating market. If you're a good looking girl, you probably get hundreds of solicitations from various kinds of men, and that's what's going on in for companies right now. But it doesn't really mean that a girl has hundreds of potential partners. There's still like 50% men and 50% women in the world, give or take a few percent. So this at some point this has to break. And the way things are going, I'm probably going to finish my own projects and get rich off poker botting or something like that before I even find a decent job. It's amazing. Yeah, I'm kind of desperate for now, but not so much for money, but for acceptance. And I can get that in different ways. I can get that by my own project succeeding. I don't need people to, compliment my work. I mean, if I could join a decent company and get paid over $100,000 a year, that would satisfy me. But in the absence of that, I can just work on my own projects. And if you're, desperate and in such a situation, I suggest you just, work on your own stuff and let the current thing blow over. The job market will recover, but much like I cannot rely on the Cutlass authors or the job market itself completely. I have to do my own thing in order to improve my skills. Programming is the kind of thing where you gain benefits by consistent practice and especially accumulation. Because I have this a library, and it has been built over many months. I have the language; it has also been built over the years. And at some point, I'm probably going to figure out the secrets of intelligence and conquer the world that way. My intuition so far is that machine learning is pretty much useless. Even though I learned machine learning, very little of it is of actual value. Instead, what is of value is these tools that I am developing. I am looking for AI, but what I'm instead finding is good programming. Now let's go back to this. I'm going to pause this and get rid of all of these errors. Be back in GV. Okay, I finally got them all out of the way. There have been a lot of changes. And I think if we don't get a positive result from this test, if we don't get a reduction in registers, I'm going to undo all of this because it's really increasing the complexity of the whole code base, and we might get incorrect results for code that has worked properly previously. So let's see. Let's just close all the tabs. Let's go here. And I'm pretty sure this should work properly. But some of the other stuff might be broken due to this. I'm especially thinking about those row gather functions. They could be broken by this particular optimization. And I don't have the... I cannot spare the effort to actually go over the entire code base to make sure that this optimization is right. Right now we're just investigating how the asynchronous loads work. Did I build this? Okay, now let's run this. We had 32 registers before. Duration 25. I have to admit that this is a lot of registers for a kernel like this. Maybe it's rolling it under the hood. We're probably going to have to check that out. Okay, now let's close it down. And we still get 32 registers. So in other words, why are we even doing this optimization? Like, it kind of makes sense. Where is the diff thing? Okay, let me just back it up. Copy. We can copy one of them. Okay, now let's clear. Now we're back. Let's copy this here. Actually, I forgot which one was which. Let's just select this, cut, paste. So there are 7 additions. R8. I mean, it's just some of these terms have changed a little. I'm not sure what this final instruction is supposed to be. I mean, what this last operand is supposed to be. The first three are the registers, and this is the integer multiply add instruction. It multiplies two numbers together and adds another to it. I'm guessing this is a constant. Or rather, maybe the one of the multiplicans is a constant. Like, yeah, we have the blocks per thread as a constant. Oh yeah, why do we have so many of these? Yeah, so many of these multiply adds. Like, could it really be unrolling the loop? Okay, here we have the nanosleep. How many do these? Oh yeah, we have the 4 nanosleeps. And that's because the innermost loop, let's see, this one, yeah, this one, it gets unrolled 4 times. That's pretty much clear to me. So do we have nanosleep anywhere else? Yeah, we don't. So it's not real. So it's not unrolling the outermost loop in order to interleave the memory loads with computation. It seems like it can do it just fine even without that. Yeah, I'm deeply impressed by the Cuda compiler technology. I really wish I knew. I really wish I understood better how it actually works under the hood. And this is basically my limitation as a programmer. I could really benefit from working with somebody who knows the hardware better under the hood than I do. Right now, I do know what good programming is, and the good programming that I do has a lot of overlap with getting good performance out of the kernel. But it's not like it's a perfect overlap. In order to actually get the optimal performance, you do need to understand how the compiler works and how the hardware executes the instructions at a low level. You do need to understand the compiler well enough to anticipate what kinds of instructions it will generate. I personally am not at that level, even though I could be very useful. Even in a GPU programming job. I'm actually yet to find one of those. I tried applying to some Silicon Valley companies which work on compilers for AI accelerators, but I didn't even get an answer. So I do feel like I am not well respected enough. I mean, I have different. I kind of getting treated as a faker when my skills are pretty good. There's no justice in this world. But yeah, you do need to have a plan if all else fails, and that plan for me is creating poker bots. Yesterday, I went into the TinyGrad repo on Discord. Okay, I'll show you. I wasn't going to show you in this video, but I'm going to show you. I made this Span language showcase, and this is like a mini tutorial. I've also posted it on the machine learning subreddit and the what. I also posted it on some other Reddit. Yeah, over here, and let's pause just for a bit. Yeah, and yeah, on the machine learning subreddit and on Hacker News. But on Hacker News, it's very easy for it just to get. There are so many fucking submissions, and only so many people who are checking them out. Like, so it's kind of easy to just fuck founder mode, working fuck off mode. Okay, what's that? Okay, this guy is great. I'm going to get back to this and read it. Everyone and their mother has something to say to a SaaS founder. Oh, you don't have a TikTok strategy? Fuck off. Have you integrated segment, postcode, and mix panel? Fuck off. I have no idea what these three technologies are. Have you done market research to figure out your pricing? Fuck the fuck off. Meanwhile, Reddit is full of these clowns debating freemium versus free trial like it's life or death. Just pick one and stop shitting your pants over it. Seriously. Stop adding your shit to your plate. Learn to say fuck off a lot. You're a startup. You're a founder. Fucking act like it. Grow some fucking balls and stop jerking around with the latest hot take from some LinkedIn thought leader who counts the likes on his posts on LinkedIn to keep his fucking pride intact. Okay, yeah, okay. Okay, I don't want to spend all this time. But basically, I gone to this Stalingrad repo. I made this whole tutorial just for them. I even went to Discord and posted that there, and I've gotten banned. Like the very first question that I got then was them asking me what's the point of this and whether I'm looking for a job. I mean, I am, but that's like maybe 5% of my purpose here. I did get a suggestion to go into the Tinygrad community and maybe get in contact with them to see whether there is any value in Spiral. Maybe we could, work something out, because Spiral is a language for making ML libraries. And that's why I pretty much designed it. I started work on it in late 2018, actually 2016, sorry about that, to create a machine learning library. So, if you're somebody who's working on a machine learning library, maybe you'd find some value in it. But I'm pretty much getting treated like an idiot. And, maybe if everybody else is convinced that I'm an idiot, maybe I really am. I think once I finish those poker bots, I'm going to go to... There was a forum where I'm going to find a community where people who do poker botting congregate and maybe offer them my services. And I think that's going to go a lot better. Like, here I have my own language, here I have my own machine learning library, here I have the poker games that run on the GPU. I also have the machine learning library running on the GPU. I have a counterfactual table algorithm running on the GPU. I mean, if you and those guys treat me like a moron, I don't know what I'm going to do. I'm going to flip. Like, there has to be at least one person in this world who recognizes the value of what I'm doing. Like, I work on this language for many years. It's not that easy to make. It's not something like you could find somebody off the street to do. Okay, so now let's go back to this. So it's not unrolling this loop. That rematerialization optimization didn't make any difference at all. In fact, we are getting just pretty much completely the same code. And yeah, you'd expect this optimization to be done by the Cuda compiler if it's any good. Like, why keep something in a register that it could just propagate directly? And yeah, it's doing that. So, I don't know. At the very least on this example, we aren't getting any benefit at all. We're getting the same number of instructions, and it's not really just, the block index x. It's actually, it does require an integer multiply add, because it needs to add the thread index, then it needs to multiply the block index by the block size, and then it needs to add those two together. So it's not really a straightforward common sub-expression substitution operation. But at the very least, for something like this, you would expect the Cuda compiler to be able to get the optimal result, and it's in fact doing that. Okay, let me just post in that discussion. Um, I mean, let me pause here. Yeah, I wrote this. I'm testing. Wait, did I reply to myself? I didn't mean to do that. But whatever. I'm testing this optimization out on some simpler cases, and as far as I can tell, the Cuda compiler is very good at optimizing array indexing. I cannot see any difference in register liveness or the instruction count. The last operand of the integer multiply add instruction, which is a constant, surprisingly keeps changing between different versions, but I cannot see any benefit in applying this. I cannot see any benefit to applying this optimization by hand. So yeah, we did an experiment and it gave us a negative result. So we're going to undo all of this because it might it's increasing the complexity of the code base for no good reason. Of course, the only benefit from actually doing it by hand is that you are guarding against the Cuda compiler, not doing the optimization properly. But personally, I don't care about that. Like, I'm not that anal about getting the top performance. That's really the job for Cutlass library authors. I think maybe it was the case that the compiler didn't apply this optimization in the past, but as it got better, now it's doing it. That's the most likely explanation for why they are doing this rematerialization manually. I mean, when you're doing optimized kernel like the Cutlass library authors are, you have to think of all the cases. For me, I'm really concerned not about just the end result, but the way I'm getting to it. Like, it's not acceptable for me. Like, if I could get a tiny bit of performance improvement for a large increase in complexity, I don't want that. Not in my code base. Performance and code complexity is something you have to trade off. Sometimes you want. It's actually preferable to have a program that's lower in complexity, even if it's slower. And in fact, this is pretty much the entire value proposition behind the high-level languages like Spiral. There's no point in using Spiral if you're just going to create some mess. Do that in C++. Okay, now what I'm looking for is the loop module. Here it is. And we still have, because we undid everything, we also brought back the bug. Yeah, now it's right. Oh yeah, it won't be a good idea to rematerialize it. This. The rematerialization optimization. The one here. Okay. I cannot see any benefits from applying it. Oh yeah, that's basically it. And yeah, it's been a fun morning session. What I'm going to do is I basically showed you how, when you have this, how the nanosleep ends up taking the entire duration of the kernel, and how the Cuda compiler is insanely good at actually interleaving memory loads and computation. So what I'm going to do is go to here, and I'm going to basically start lowering this nanosleep iteratively, and I'm kind of going to make it so that there is a, you have to have a split between memory loads and computation. Right now, it's entirely computation. And once I get it to, have split between the memory loads and computation, we should be able to start seeing the effects of actually interleaving the loads and computation using the asynchronous loading instructions. I want to see at what point the asynchronous loading instructions give us a benefit. I want to understand that. And once I do, we're going to I'm going to show that to you, and then we're going to do some work on optimizing the matrix multiplication kernel. Who knows? Maybe when I implemented the matrix multiplication kernel at the start of the year, I was using the Cuda toolkit version 12.3, and now 6 months has elapsed and it's at 12.6. So maybe we'll be getting better performance simply due to that. I've sent that Cuda, Lidac training example. Maybe they used it as a reference to optimize their compiler a bit more. A lot can be done in 6 months. We'll see. Okay, so I'm going to go have breakfast and see you later. I've managed to figure it out. Let me show you. First of all, in the previous video, back when we were getting 32 registers and 40 for the final test, the debug mode was turned on. What I've done is reorganize all the tests. First, we have this config file. And these are just some constants. Also, I factored out the nanosleep function. The reason why I did all of that is so I can make sure that all the tests are using the same constants between them. I think, actually we haven't, I don't think I made a mistake, but it was a possibility that some of the issues in the results that we were getting both today and 6 months ago were due to the different test setups. So over here I'm making absolutely sure that everything is in order. And here is test 0 again. The main difference that I made is I replaced the multiplication with an addition here. This is to make absolutely sure that this is pretty much purely a test of memory transfers. Now this test 0, this is just a regular map that I showed you earlier. And this tests how much the memory transfer takes. Let's compile and run it. Build file. Ignore what's here for now. And this should take about 9 milliseconds. 9.5, something like that. It's actually close to 9. The memory throughput is 91.5. The number of registers is 26. And yeah, this is basically how much the kernel runs. Just the 9.1 milliseconds is, you can think of this as the time it takes to read and write from a tensor of size 1 gigabyte. It pretty much tests how long it takes the GPU to go over 1 gigabytes of memory. Now this test, immediately after that, tests how long the nanosleep function takes. The number of loops here is the same as the number of loops in how it in the map kernel. So let's try this out. We'll build this, then we'll run it, and we should get 11 milliseconds, close to that. Oh, really? 12. Actually, I think I should be closer to 11. Let's try it again. Let's try it again. Yeah, okay, now we see 11.2, something like that. Yeah, it varies depending on the GPU's mood, but it's around this figure. So if we think about this from a logical perspective, the minimum amount of time the kernel can run, if we are doing both the nanosleep thing and reading and writing from memory, is 11 milliseconds. If we overlap the computation and the memory loads and stores perfectly, we cannot do less than it takes it to compute, and we cannot do less than it takes it to load and store from memory. And the maximum of that in this case is how long it takes it to compute, and that ends up being the minimum runtime for the kernel. In other words, we cannot do better than 11.19. So now we have this asynchronous loading version. We're going to compile and build it. If the Cuda compiler wasn't doing a good job, we'd get something like 20 milliseconds, which is what you get when you don't interleave memory loading and storing the computation. And the Cuda compiler is actually amazingly good at interleaving memory loads with the computation, even in the synchronous version. It's very impressive. Actually, I thought it would be a lot better. Let me try this again. We do get 26 registers, but I think that running this again should give us a better result. Okay, 12.6. For some reason, when debugging is actually turned on, it does a lot better in terms of performance. I don't get that at all. I've got an 11.5 when debugging is turned down, when it needs to execute those asserts. It's really amazing. So yeah, I don't really get this, but I don't know why the performance is so bad. I expected it would be something like 12.5 instead of 15. Okay, let's assume it's 14 here. I don't know why it's so bad right now. I remember back in 2015, when I was working on my very first ML library, I was testing some recurrent neural network models. And one day I'd get something like 4 seconds to run, and the other day I'd get 3 seconds to run. And it was the same code, no difference at all. I couldn't understand it at all. So, okay, we built test 13. So let's give it a try. As you can see, there are 26 registers, and now there are 23. And the duration is 12. Let's try running it a few more times. .59. But as you can see, it is better than the synchronous version. Okay, we even got 11.55. So it's very good at actually interleaving the memory loads with the computation. We can definitely see an improvement in register usage and the time it takes it to compute the kernel. In other words, I thought that the pipelined asynchronous loads didn't work, but they clearly are working here. So what you see here is in fact the way to use the asynchronous loads. Okay, let's try it one more time, and then we'll move on to the last test. Yeah, so it's 11.5, 12. It's a bit worse than actually just running the nanosleep function, but it's actually it kind of varies, but it's very close to that. And this does give an improvement in registers and performance, which is something that I didn't really understand. I thought that it wasn't doing that. And after that, let's build this. After we finish the test 4, I'm going to show you how it works with the debug mode turned on. Yeah, this is pretty awful. The number of registers is 24 instead of 40 like it was before, so it's better than asynchronous loading. But as you can see, this duration is very bad. It's much worse than for the previous version. Oh, now it's 17. Oh yeah, this is actually even worse than it was before. This is how I thought that the pipeline loads should work, and for some reason they didn't really work in the matrix multiplication. And maybe the simplest explanation is that I kind of messed up the testing somehow. That's what I'm leaning towards here. Because logically, I mean, it's not logically, but I cannot really think of any better way of doing the pipeline loads like this. There simply isn't any other way to do a map kernel like this, and it's very similar for how you do it in the matrix multiplication kernel. You have this initial load, and then the consumer phase, and then the producer phase again, for when the future I is, or when a future iteration exists. Okay, let's go to base. Let's turn the debugging on. And I'm going to, let's say, build this, build this, build this, build this, build this. Now let's go from the start. This first test is just testing the memory loads. How long does the memory transfer take? 9.42. It takes less than the computation. How long does the computation take? 13.52. That's a bit long. Let's try this again. $11.71. $12.82. I mean, it's kind of a lot worse now. I've seen it take, we've seen it take close to 11. Okay, so it's kind of close to 12 now for some reason. Okay, let's try test 2. Synchronous loads version. Now we are testing the map kernel with the synchronous loading, and yeah, this performs insanely well for some reason. I cannot even begin to guess as to why. Maybe it's unrolling the loop once or something. I don't know. I mean, this literally performs better than with the debug mode turned off. 9.5. Yeah, it's for some reason the compiler does a job that's actually too good here. It's so good that it makes all the other tests bad. Okay, now let's take a look at the asynchronous loads. And this thing here is basically what was confusing me. I'd run this and then get worse results than with the synchronous loads. You really need to make sure to turn the asserts off when you're running these tests. Yeah, now it's actually worse. It's 32 registers. In other words, there is no improvement on the registers, and we get worse performance. I guess having the asserts in that producer phase and the consumer phases is messing things up. So yeah, it's pretty bad. And if we go to the last test, we'll get 40 registers and even worse performance. Yeah, it's worse. For some reason, the synchronous loads can be insanely performant. Maybe having asserts in there allows it to do some special optimizations that it couldn't otherwise. That's the only explanation I could have for why it's so good now. So, okay, we're going to. I don't know. I guess we are pretty much done. I mean, with the asynchronous loads. And what we have to do. Okay, I won't actually bother replacing the map in the primitives kernel with this. We could replace the map that's currently inside the library. With this thing, but we aren't really using the map anyway, and there is not much. There isn't such a big difference in performance that I'm just going to leave the map that is currently in the primitives module there. Yeah, I forgot to remove the comments. Let me just test 2, test 3. And I'm going to leave a comment. This version works. But only. Right now it's true. And I'm going to leave a to do. Replace the primitives if anybody wants to, do that, you can leave a pull request and I'll accept it. So we've come to a conclusion. this is the best version, and this is how the pipeline loads should be done. And we should be using this version in the matrix multiplication kernel as well, because it will use less registers and will get better performance. Here the performance was pretty much optimal, as we'd expect. We only see the duration of the computation, and the memory loads are perfectly interleaved with the computation. I think if I turned off the debug mode, if I made sure it's turned off, and then if I made sure it's turned off, and after that put this kind of code into the matrix multiplication kernel, we should see a significant increase in performance. Right now, when you try to run it with a small kernel, you see that it kind of ends up loading. If you right now, let me show you. It's easier for me to show it to you than to explain. Let's first do the full metrics here, and once we go into detail, we have a certain tab here. I think is it PM sampling? Oh yeah, it's right here. So right now it's measuring this over 12 milliseconds. But if we go even if we run the kernel for last time, and if we instead of if we run the matrix multiplication kernel for something like for a fraction of the time with a small size, you'll be able to see peaks and valleys here. Like you'd see a peak where it loads for a tiny amount of time, then it does. Then over here, actually up here, you'd see it compute. Then it loads again. Then it computes. And this is why we get only 50% utilization of the GPU. If we could instead interleave the data loads with the computation, we'd be able to get much better utilization. And that's what we are aiming for, and what we couldn't do right the last time around. The only difference this time is that I've done the basic sanity checking to make sure how asynchronous loads actually work. So I think we'll end the video here. In the next one, we're going to revisit the matrix multiplication kernel. We're going to do all the testing from the top. We're going to make sure that we are first going to go over the loop unrolling, and we're going to make sure that it's not unrolling this very large loop, because that will blow up the code size, and that will cause issues when it's used later in the ML library. And after that, we're going to replace these initial loads from global to shared memory with asynchronous ones. We're also going to, I guess, are we going to replace the linear loop here? I'm not sure. Yeah, we're going to have to do something to make sure that the iteration is basically like with the look ahead loop. We have to make sure, we have to get the information whether the loop is initial, what the current iteration is, and what the next iteration is. So we'll probably just implement a look ahead linear loop, something like that, to take care of that. And that should be it. After that, we're just going to bring that into the machine learning library. Oh yeah, also this config sheet that's currently on the type level. We are going to fold that into the config using existentials, because right now it's very ugly. I cannot bear to look at it. We're also going to do some work so it automatically this M tile, N tile, and K tile, those are the tiles of the in shared memory. And if we are operating over small matrices, we don't need such large tiles. So we're going to enable support for a lot of smaller tiles. Yeah, we definitely need that, because right now, especially in the final layer, we're calculating too many actions only to throw them away. I probably get a reply from the Cutlass author next week. If I don't, then so be it. I guess I'll be busy. I have to go to the doctor. I'm still actually struggling from my repetitive strain injury. I finally figured out what's wrong. I think what's wrong is that I went for a X-ray and they discovered calcificates in my right shoulder. So I'm probably going to go to the shockwave therapy or something else in the nearby future. And after that treatment, hopefully I'll get back to my usual self. Oh wait, accidentally put this here. Okay, so thank you for watching. And we're going to continue this in the next video. I'm really happy that I took the time to investigate asynchronous memory copies. I thought that there was something wrong with them, but it turns out that the whole time the Cuda compiler was a bit too good with synchronous loads. But when we do the synchronous loads properly, and when we turn off the debug mode, it does perform better than the synchronous loads. It also improves the register usage significantly, and given how much registers the game and how much register usage the game itself is using outside the ML library, we definitely need to bring that down as much as possible. Also, using the asynchronous loads will allow us to not have to unroll that that middle loop so much. That should also help greatly. So thank you for watching, and I'll see you in the next video. Bye bye. Please like and subscribe. Don't forget that.